Hey there, in this video I want to talk about how scipy optimizes functions. So in optimize we have a function called minimize, and if you look through there, it sort of seems like, hey, this should be the one I use to calculate minimize, and it is. The difference here is we have minimize and we have minimize scalar. We already looked at minimize scalar, how it does things like golden ratio for us and close cousins of that. It's for 1D functions. Minimize is for 2D and more functions. I mean, I guess you could probably make it work with 1D functions, but it's also kind of overkill. By default, it uses a technique that's basically gradient ascent with a little bit of optimizations to it. But there are actually quite a few different methods this thing can call. If we look at the documentation, we can feed it a function. It wants x naught, which is a starting guess. It's going to be an array of values if we have a multi-dimensional function. Most of these arguments we're not going to need to mess with, except maybe method. And if we scroll down here, we can see method is going to be a string naming one of these many things. There's a total of 14 things in this list. And if you're wondering, like, why don't we just use the best one? It's because there really isn't a best one. It really depends on what function you're trying to minimize. Some of these will be faster than others, some of them will work, and other ones won't be able to find the minimum that you want. In my experience, the default method is pretty good. Another one I like is Powell, which is kind of based on golden ratio, like a multi-dimensional golden ratio. Those ones are pretty good. But really, depending on the problem, every problem has better and worse ways to solve it. So you might have to do some experimentation here with the different methods. So let's apply this minimize to the function sine x sine y. First thing we need to do is write a Python function for that. And it needs to have a single argument, which is an array of all the values, which means that inside we probably want to do something like tuple unpacking to pull apart the individual x and y out of that array. And then for our return, we can return the single value sine x times sine y. Now here in our minimize, we're going to give it the function, and then we're going to give it our initial guess, which is technically an array or anything that Python can turn into an array. So we could use a tuple, for example, or a list. To match the example we did in the previous video, let's check to find the minimum that is closest to 0.1, negative 0.1. And that should be pi on 2, negative pi on 2, if everything works. So if we run this, we can see, just like minimize scalar, we get this whole big object that pops out. And in there, it prints for us the best value, which is pi on 2, negative pi on 2. We also see it only took 3 iterations, which is like mind-blowing that it could do it that quickly. But this is not like a floating point value I can assign to. So like with minimize scalar, we need one more line here, which is we can put that object in something called result, and that result has attributes. And if we tab here to see what those are, I haven't run the cell yet. Okay, so run the cell. And then I can tab here to see what it doesn't want to show me. I can shift tab then, at least to see the things that are in there, and the one we want is called X. I thought tab completion would have helped me there. In any case, that's going to give me my values. In this case, they're going to be in an array because it was a multi-dimensional function. Let's try the same thing here with a different method. So instead of using the gradient descent, we're going to use something that's based on golden ratio called Powell. And I'm going to show the whole result object because I want to show you that although we get the same value at the end, I mean within rounding error, this one took a different number of iterations. It's not always going to be less, so it's not like, oh, Powell is the best. In this particular function, yeah, it was more efficient. Only 2 iterations to get there. In other cases, it'll be slower. In other cases, it'll give you values that aren't quite right. It'll kind of get stuck, so to speak.